Okay, good. So let's start. So one of the tasks I wanted you to do was to see if you could derive this. Have you managed to do that? Anybody? Or you are confident that you should be able to do it? Did you try doing this at least? Getting this expression? Look, the point is as follows, that if you don't try doing this, I cannot go fast and you will have much less content in this course. So the amount of content depends on how much you also try to keep up with the lectures. But if you say that you would be able to do it, then I don't need to do it. Anybody who says that I have to show how this happens, let me know. No, I don't like this silence. Tell me something, at least give me some feedback.
Sir, we will try and show you in next class.
No, that's useless. Don't say that. You should have done it this time. Will you be? I don't. We cannot. We don't have time for it to do it in next class. So tell me whether you should actually do it now or not. Okay, let me do it now. Anyway, this is simply, we simply go slow like this and we cover less content there. So anyway, so the thing is that the theta of t, the Fourier transform is simply like this. We know this already. It's plus I epsilon, I guess. So if I, for t greater than 0, I should close the contour in the lower half, because if t is greater than 0, then imaginary t has to be imaginary omega. Sorry, if imaginary omega has to be negative in order that this is damped at t greater than 0, right? So I have to close it down, and then it would require that I should take this contribution. So this is correct, I think, right? This is correct.
Sorry, in my notes it is minus theta of t is this.
Hmm?
In my earlier notes, it's minus theta of t is this. Might be wrong.
Minus theta of t. Okay, let's see. Yeah, probably you're right. It should be minus because I'm closing the contour in the lower half plane, right? It is clockwise instead of anti-clockwise. That is why we need this minus. You're right. So this is this theta of t. Now we need to use the convolution, right? So okay, so basically we have the GR is GRT is equal to minus I theta t. I'm just writing t minus t prime as t because I can set t prime to 0. It makes my life easy. And then sine of omega naught t, right? That's what I found out in real time. Sine omega naught t. Probably there are some other factors I missed, haven't I? Isn't there something else I should have had that I didn't write down? Or, oh yes, I did forget. This there is of course this minus I minus I h bar by m omega naught, and I think this minus factor also should go away probably. This minus factor, this minus I factor goes away. It is, yeah, this is what we found out. Like last time in real time, this is this h bar omega naught m omega naught. There is also minus I factor already inside this. So this is why when you define dr, that cancels this overall minus factor and take the commutative. So this is this expression, and we want to take the Fourier transform, right? And the Fourier transform is defined by convolution. So so this is the convolution that we should use. If in real time, if it is ft gt, the Fourier transform of this should become d omega by 2 pi f omega minus omega 1, or d omega prime if you wish, and g omega prime. Okay, so this is what we should have. And then if I put in this theta, the Fourier transform of theta is minus, the Fourier transform of this is okay, this tells you the Fourier transform of theta is it is 1 by minus 1 by 2 pi I times omega plus I epsilon, right? Inverse. Yeah, so therefore, if I substitute it here, I should get d omega prime by 2 pi, then here 1 by minus I, and then I have 1 by omega minus omega prime now here it should be plus or minus epsilon. So I just simply replace omega with omega minus omega prime, and then I get, yeah, plus I epsilon and g omega prime. And what is g omega prime? It is sine omega naught, right? The Fourier transform of sine omega naught t. The Fourier transform of sine omega naught t is simply delta of omega plus omega naught minus delta of omega minus omega naught by 2i, right? So you see that here I get I times minus I becomes 1, and I simply get omega minus omega prime plus epsilon, right, by 2. So there is also an overall factor of h bar by m omega naught, which I should write down. So if I put that in, so the first factor delta omega plus omega naught gives me simply, if I substitute that, and there is, okay, there's a factor of 2 pi which gets cancelled, sorry, because the Fourier transform of sine omega naught t is 2 pi delta omega plus omega naught minus delta omega minus omega naught by 2, and there's an overall factor of 2 pi. So this 2 pi gets cancelled with this 2 pi, and we have an overall factor of half, and here, and that explains how we get this h bar by 2m. This extra factor of 2 comes from this half of the sine, and then we get this. Okay, is this clear now? So is it clear that how I got how this comes about now? Okay. All right. So this is the Fourier transform of this thing, which is very important because you see that you have the poles. If I look into the poles of omega, in omega, it is simply at the propagating frequencies, omega naught, and both are shifted. It is at plus omega naught and minus omega naught. So this is omega naught minus I epsilon, and the other pole is at minus omega naught minus I epsilon. And both the poles are in the lower half axis, right? So essentially what we are doing, so you can think of these as propagating modes for every value of k, and we get this contributions, and it simply picks up the poles at the two propagating values, and they are minus I epsilon, and this shift in the upper half plane, lower half plane simply implies that this will contribute only for t greater than 0, right? Because if I do a Fourier transform of this, And for the same reasons that we said earlier, like for here, if I do a Fourier transform of anything e to the power minus I omega t, it has some poles. For t greater than 0, I have to close the contour in the lower half plane so that I can dampen the contribution from the from the circle at infinity, semicircle at infinity. And then only these two poles will contribute, right? Both these poles will contribute. Is this clear? And for t greater than 0, to dampen the contribution from the circle at infinity, for t less than 0, I have to always close it in the upper half plane. And if I close it in the upper half plane, there are no poles, because both of these poles, there are only two poles, and both of them are the lower half plane. So therefore, it will not contribute. So it's clearly G. So essentially, one of the important thing is that GR omega is always analytic in the upper half plane. It's a very general statement. It is always analytic in the upper half plane. That simply comes from the fact that the GRT, because of the theta function, is going to vanish for t greater than 0. So all the poles and branch cuts of GR, of the retarded propagator, has to be in the lower half plane and not in the upper half plane. So that's one of the very crucial statements of this thing. And this is all evident here, but it is a more general statement than this. Okay. So let me already tell you what is going to happen in the interacting theory. So this is also true for quantum mechanics. So you have GR omega will be h bar by m omega naught, right? And omega. Okay, let me put so suppose I go to suppose you are having a k index for the oscillators. Remember that the Hamiltonian is simply a collection of oscillators, each labeled by k, and you have some k, h bar omega k, and instead of omega naught, you have omega k and a dagger k, ak, right? This is what you have. All right. What you get is that if you look in a general interacting theory, what happens is that you expect a structure of this kind. So if I just look at a single K mode, it's exactly like a harmonic oscillator and it's decoupled from everything else, right? It's simply a collection of decoupled harmonic oscillators for K. But suppose I add interactions now, right? If I add some interactions, then you will mix different K modes. All right. So what the general structure of it would be like this. You will have h bar by m omega k. And then you will have, let me put it this way, you will have something called, okay, you will have omega k. And then the rest of the correction of the interactions can be put into two parts. It's a self energy term. And this will be a real omega k and minus plus I imaginary sigma k. So now I can get rid of the plus epsilon term for reasons that I will say later. And then, so this is this thing that we get from here, minus of this, omega minus omega naught minus epsilon. And that, okay, the minus sign comes from, you know, the thing of the sine omega naught t, if you remember. So plus 1 by omega naught. So this is, so minus 1 minus omega naught and plus omega minus omega naught. And this is h bar by 2m omega naught. Sorry, I forgot to write 2m omega k. So this should be minus. And so this is all inside this thing. And then you have plus omega k. The same thing, plus real sigma k.
So what is sigma k? Could you repeat again?
I'm explaining that. If you hold on a minute, So I have to just see the poles are is at omega naught k. If you remember, this omega naught k I'm simply referring to as the thing that appears in the decouple, sorry, in this free theory, where the particles are not interacting. And then this is what I call the self energy. I'll explain what it is a little bit. Hold on. So you have omega naught plus real, and this is omega naught minus omega, and then plus I, and here also it is plus I imaginary sigma k. Exactly. So now where are the poles? Okay, let us look at the poles and then I will explain this. So the poles are at omega, the poles of this function are at omega naught k, which was in this, for the free theory, it was here. And then there is a plus real sigma k, all right, and minus of I imaginary sigma k. And the other pole is at minus omega naught k, minus of real sigma k, and plus I, sorry, the same, minus I imaginary sigma k. So what is the difference? The difference is as follows. So previously it was just below this, it was omega naught k minus I epsilon. So it was just a little bit displaced. It was almost on the real axis. But now you see there is a shift. There is a shift of this thing somewhere here. So let us say now it is somewhere here in the interacting theory. So maybe I should do some new colors. So previously it was there. Okay, this color looks very similar to this color. Maybe try to. So previously it was here, very close to the real axis. It was only minus I epsilon shifted downwards. But now the shift of both poles is at minus, the imaginary parts are shifted by minus sigma omega k, right? Whereas the real part also have got shifted a little bit, all right? So what is this telling you? What's the physical interpretation of this? So firstly, you see that if I go to, if you can plot the real and imaginary parts of this function, how they should look. How will the real and imaginary part of this function would look? Okay, so if I take imaginary, maybe I should go back to the original color now. If I look at imaginary GR, right? So firstly, I am assuming, so first of all, it's very important that this imaginary part of the self energy is greater than equal to 0. So that is very important. Otherwise, if that is not the case, then basically the interpretation is that your retarded response has to be always positive, right? Now, if your imaginary part is positive, what it means? It simply means that if you go to real time, you have to have a growing response, right? So suppose, okay, so if I go to real time and take a contribution from the pole, right, how this is going to look. So that's an important thing to first understand before I go to this thing. If I go to in real time, the response is going, yeah.
Plus imaginary sigma k is greater than 0. Like imaginary part of sigma k is greater than 0. That's the condition.
Exactly. That's the condition. Here, no, not plus I. It is the thing is shifted here, right? So you need these to be greater than 0. Okay, you need these to be greater than 0. All right, so yeah, so this is, I could have written it, the whole thing I could have written it just as sigma k, and then I'm splitting it into real and imaginary part, right? I don't know why I wrote this as real sigma k plus I imaginary sigma k. The whole thing is nothing but, sorry, maybe I should have, 1 second. Let me fix this properly. Yeah, I think the convention is to write it in this way. Let me put it as plus. So okay, this is simply a definition for the moment, right? And so what I'm doing, I'm writing at omega minus omega naught k plus imaginary k, sigma k, but sigma k is a self energy. This comes from the interacting theory, okay? So basically this is coming due to the interaction. So there will be still a pole, but the pole is not exactly at the pole of the free theory, okay? And then, so this is the structure that you expect without doing any calculation, right? So in the interacting theory, okay, so let me explain this a little bit in a clearer way. So in the non-interacting theory, you had two poles, which was this omega naught k plus minus omega naught k, and they were all displaced below the origin a little bit. So to give you the retarded response, right? It was just a trick to give you a retarded response. Now in the interacting theory, what you expect is that these poles would be modified when you computed the retarded response because of the interactions of the other particles, right? This is what you expect, and the way it occurs is that if you take simply a one particle state, it will mix with other particle states in the middle with this virtual cloud. And this virtual cloud, what it does is that it shifts the location of the pole, and this contribution to the pole is from the other particles is called the self energy term. This is called the self energy term. And similarly on the other side, you also get this minus, maybe I should use the conventional thing. So this is, one is omega naught minus real k, and the other word would be omega naught minus real. So, so this is again plus I, and then this is simply plus. Okay, let's see this. This is plus. So what are the contributions? What are the poles now? The first pole is at omega is equal to omega naught minus real sigma k and minus I imaginary sigma k. And the other pole would be at minus omega naught k plus, sorry, this is minus omega naught k minus real sigma k again. And sorry, this is, yeah, this should be here. This should be at minus real sigma k plus I imaginary k, and this is yeah. So this should be then plus. Yeah. Anyway, the main point is that you expect the real parts to be still like this: omega naught k minus real sigma k and minus omega naught. So the real parts are simply just simply negative of each other, but the imaginary part are both shifted downwards from the real axis by the amount imaginary sigma k. So that's the structure you expect intuitively, and I'm going to explain why you intuitively expect that. But this will not be all. You also expect some other contributions to this, and essentially the other contribution not comes from poles but from collective excitation, from multi-particle excitations plus branch cuts. So the general structure is as follows. Let me explain. So suppose I fix some momentum k, and I try to look at the structure of, so k is the mode, k is a particular mode I'm looking at of a harmonic oscillator, and then k for k is equal, for if I fix k is fixed, mod k is fixed, and I study how the poles and branch, and I look at this is real omega and this is imaginary omega, and I look at the structure of gr omega k at fixed k, and it should not depend if it is if there is rotational symmetry, then you won't expect it to depend on the direction of k, but only in the on the magnitude of k. So you expect that you will have things like this. You will have some poles which are close to the origin, and then if you go far away, you will see some branch cuts of this kind. So I will explain what is the meaning of this branch cuts and why you have this branch cuts. So let me first tell you what is about this particular poles. So these poles are essentially the response carried by the individual single particle states. So these are the carried by the individual single particle excitations of the system. But because you have, suppose you have already, you are in finite temperature and there's already some background excitations, the system already has some particles in it. And whenever a single particle gets excited, it should simply interact with the other stuff, right? Whatever it is there. And in fact, it can also include, it can also interact with virtual fluctuations. So all of this put together would be shifting the pole. This is something that we will appreciate more and more slowly, but for the moment, so this is going to shift both the real part. So essentially, this is the energy of the particle gets corrected. It's no longer the free energy, what the free particle would have, but this is the contribution of the interactions to changing the dispersion relation of the particle itself. So one of the things it can do, it can change the mass of the particle to something else, right? It can just redefine the mass of the particle or renormalize the mass of the particle. But there could be other kind of other corrections too, which are higher order in K. So it modifies the dispersion relation to something else. Okay, and this is what you call the real, it's a real part of the self energy. This real part of the self energy simply modifies the dispersion relation. If I do a Fourier transform of this at a particular K, so I get GR K as a function of T. And how it's going to look, if I do a Fourier transform of this, I would simply pick up the pole contribution. And essentially it would look like this. From this pole, I will, if I combine these two, right? Because there's an overall minus sign here, there is a minus here and a plus here, I will get sign. So there would be theta T minus T prime again, because I'm just doing the Fourier transform of this guy, right? And it's basically the same structure that I will get, but sine, instead of omega naught K, I also get a correction real sigma K T minus T prime, all right? But there is also a damping correction, which comes from minus imaginary sigma K T minus T prime. So if I do a Fourier transform of these together, this plus this is obvious, I should get this, right? I just did the Fourier transform for you. I'm going to doing that the inverse Fourier transform. The only difference is that before I was getting e to the power minus epsilon T minus T prime. But now I will get this, and I will get a damping factor, which is not a very small damping factor, which I can take to 0, because it's a finite damping now. This is imaginary sigma K. So now this has a very beautiful interpretation.
But
So what it, yeah, sorry.
there are more terms, right? You said like some more terms will be there.
Yeah, I just told about if I just take account of only this and this is what I get. The branch cut contributions, I'm not, there will be also more terms here. That comes from the branch cuts, which I'm forgetting for the moment.
But branch cuts,
yeah, indeed, there will be.
We'll see that later.
We will see that later. And essentially, if I go for very large times, only this single particle like contributions are important, because the branch cuts, if they're moved far down in the way, the more and more down in if you move farther and further down in the imaginary axis, they will give you more and more damping, right? So if there is more and more damping, then the contributions are suppressed at large times. So if the imaginary parts of the branch cuts are supposed to be larger, then then these things are basically like this. So you will have something like single particle excitations of the system, right? And single particle like excitations. Actually, these single particle like excitations could also be collective excitations, not coming from a single particle. So there could be some, like for example, in Fermi liquid, one of such excitations would be the zero sound. In a plasma, which is what is a plasma, is simply a collection of charged particles at some finite temperature and some chemical potential. There, the single part, these kind of well-defined excitations would be so-called plasma excitations. They're called plasmons. And these can have, then of course, there is no analog of omega naught k, because they exist because of the interactions in the first place. So essentially, this is how they look like. They would have the structure of this whole thing could be, it's something that is very well defined excitation that carries something. But if there are already single particle like excitations of the system, they should survive definitely. Why they won't survive when you go to collective medium? It's like if you have the original phonons or photons, this would be simply shifted. So it will get a real part of the self energy and an imaginary part, and the imaginary part will lead to damping this. So the interpretation is that this imaginary part gives you the lifetime of a one particle excitation. So you can think in this way: if you take an electron excitation in a single particle electron excitation in a system, so in the vacuum, an electron excitation would be infinitely well lived. The electron in vacuum never decays. But if you look at electrons in the metal, how it looks like, so you can think in this way that you have the Fermi C filled up. Of course, this is simply a non-interacting theory. You start from there. But now you suppose you put some electron on top, you add an electron to the system. Maybe that's a better way to say it.
So when you say particle excitations, you mean like creation of particles, right?
Yeah, just hold on. So suppose I add an electron to the system, I add somewhere here. After some time, what is going to do? It is going to interact with these electrons. These and these are going to interact. And after some time, this electron will manifest itself into two electrons and a hole. And the total energy would be conserved, the total momentum would be conserved, but an electron would decay into two electrons and a hole, right? So in a metal that can happen without, it allows, I mean, in quantum mechanics, anything that is allowed by energy conservation and momentum conservation that is not forbidden can happen. And this can happen, right? So you have a single electron excitation can split into two electrons and a hole, right? Electron goes to electron and a hole. It's not a positron, it's a hole. That's what I mean. Maybe I should write it as a hole. So this is possible in a metal, for example. So what is going to happen is that your electron would will have a finite lifetime, which is the imaginary sigma k. Okay, it's inverse of the imaginary sigma k. So that is the lifetime of an electron, because it will decay into multi-particle excitation. So essentially, this imaginary sigma k is a measure of how a single particle excitation. If I take a system that has n plus one particle, right, and that will simply go to. Sorry, I'm a very stupid. Suppose I have a system that has only one particle. So here, by particles I mean the effective particles. So here you can think that whatever the field C, Fermi C, I just forget, I call it the vacuum. And this is vacuum plus one particle. It's simply a one particle state. And the multi-particles are simply this electron hole excitations, right? So there could be electron and hole pairs that come up. If I excite this Fermi C, I will get one excitation here and a vacancy here, right? These are the fundamental excitations of a Fermi C. And these are electron hole pairs, right? And then you have this electron, a single electron excitation would interact with this and basically split up like this. Okay. So that is that. So basically it will mix with 1 plus 3 plus 5. It will always be odd because you need to conserve the charge and energy, and so it will always have this mix. It will go to a mixture of this thing, and but it will retain some kind of overlap here, right? And this is very interesting, and this is something that we will see. What happens is that the residue is also an exact residue here, Zk, that we will talk about, Zk, where Z is positive. So this is overall normalization. So the point is that Z of K is a measure of how well you retain your single particle character of the excitation. So Zk is a residue of the pole. And these are called quasi-particle pole. Now, why it is called quasi-particle pole? Because it's almost a particle, but not quite, because in an interacting theory, it's a long-lived, infinitely long-lived excitation. But here, it will have a finite lifetime. And basically, it mixes with multi-particle states. Even it's not a single particle state as such. And so therefore, and the way to see it as follows: we identify them with the analytic structure of GR omega K. Now, GR omega K cannot have anything, any pole, any branch cut here, because it's completely analytic here, right? It has to be completely analytic because it's a retarded response function. If this imaginary part becomes positive, the interpretation is simply that it's an unstable system. So that's the system that you started with, about which you are perturbing, is unstable, or this vacuum is unstable that you are perturbing, or this finite temperature system that you are perturbing about is unstable, because if this is positive, it will simply grow with time. So that's the interpretation. But typically, you start with stable thermal equilibria. Of course, you can have systems of this kind where suppose you have a metastable vacuum, and then it can, or even an unstable vacuum of this kind. You can have, suppose you look at the free energy and you are expanding about here, an unstable point, then obviously you can get some unstable excitations. But this is not what you are trying to do here. I'm always assuming my vacuum to be stable. So in that case, you always expect the imaginary sigma K is greater than 0. Okay. And this real sigma K is essentially the shift or renormalization included of the particle, or the notion of the particle. And Z of K is going to be extremely important also. So this is basically the residue. So in a way, you could say this way, that if I look into one particle, and with time it goes to 1 particle and 3, but the weight of the 1 particle thing, so if I look at this overlap, 1 after some time, okay, maybe a better way to put it is that this, but okay, we will make it more precise. This particular character is Z, and the rest of it would be simply square root 1 minus Z, where Z is positive. So this is up to so I can always absorb the phase here. So essentially, what is happening is, in a way, that the weight of that is still remains the 1 particle excitation, and the weight of it is proportional to Z. So that is the interpretation of this particular factor that we get here, right? That is interpretation of this factor. So it will become clear. This interpretation would become clear when I do a similar kind of, which is a bit harder to do, for the Feynman propagator. And in the context of the Feynman propagator, it is called the Callan-Lehman representation of the Feynman propagator. But this is, in the context of retarded propagator, is more physical. In a way, it's much interesting and physical. And this structure would be crucial to even understand what renormalization is, because what you can prove in quantum field theory, this has to be a general character of any 2-point function. So I'm just now making a transition from a free theory to an interacting theory. What we will see in quantum mechanics is also true. In quantum mechanics, suppose you had, there is only one K, there is no K label, but suppose you add you add x to the power 4 term in the potential, right? You will get exactly the same structure, except that there is no K label. You will simply get a Z omega minus omega naught plus real part shift in the energy. So the oscillator energy would shift, right? And this is basically the classical effect that the time period of oscillations are going to shift because of the x to the power 4 term. But then, of course, there is also this mixing term or the single one. So there would be also a width that you get. So it will have a decay time. So it would mean that because of the anharmonicity that you're adding to the potential, so you become from x squared to x squared plus x to the power 4. So if I take a single mode x omega, that is going to split, right? And by energy conservation, it can split into x plus with omega 1 plus omega 2 plus omega 3 is equal to omega, right? So this any mode can split into this 3 because of this interaction. And of course, you will get a finite width because the omega is not sharply defined anymore. It's not at omega naught anymore. You will see a split. But this is something we will see explicitly when we do the computation. I will tell you how to do this computations of retarded correlation function in the interacting case. And if you do that, you will explicitly see it coming out. But for the moment, it's simply an intuitive picture. The intuitive picture is also obvious from the statement that if it's an interacting theory, if you are at very small, if you evolve at finite time, not at infinite time, the energy is no longer conserved. So if you start with the oscillation with energy omega naught, its energy is ill-defined at finite time, right? So you should have a branch of all possible energies. So in a way, you could think in this way. I take, if time rhymes this way, I start with a single mode omega naught, and that's not going to be, energy is ill-defined at intermediate stages. So I should allow this x to the power 4 vertex, this x to the power 4. So it's important to see the story first and then see the math later. So the story is simply this: the x to the power 4 vertex leads to a split of this thing into 3 possibilities, omega 1, omega 2, omega 3, such that the energy is conserved. And the energy conservation is taken into account simply by, because we're ultimately doing all integrals from minus infinity to infinity. And if you don't do that, then of course, you won't, this energy conservation is also not there. But okay, it's a good story to do like this. And then they recombine again and you get this. If you are waiting for a long time, energy conservation again would hold, and this is something that you expect if you wish. But I will make this story more precise. And essentially, this leads, if I cut at a finite time, I would see mixing with. Okay, there could be processes where nothing happens, but there will be a mixing of this thing, right? But there can also be mixing with many more because each of these 3 things can split, right? And some of them can even recombine into like this way. Let me draw it again, maybe. So suppose they split, this splits into 3, this splits also into 3, but these 2 recombine and create 2 others, and you can have all such possibilities, right? So you will, if you cut at a finite time, you will get all possible kind of multi-particle states, and so it will be superposition of all of these things happening together. And this is what gives you a finite lifetime to the one particle excitation, because it can decay. There's a probability amplitude to decay into other stuff. And essentially that it is. Now, one of the ways to measure the strength of the interactions, one of the measures to say how strongly coupled my theory is, or how strongly interacting my theory is. So intuitively, it is clear that this Z should lie between 0 and 1, right? because 1 is the maximal possibility. It is 1 when there was no interactions, and then it should decrease from 1. But the poles have to have positive weights, right? If there are no positive weights, then I don't get back this kind of a structure. So what you expect, so intuitively you expect that this should be true. And when z of k vanishes or goes close to 0, this is exactly when even a quasi-particle picture breaks down. Okay. And one of the interesting thing is that as long as this quasi-particle picture is valid, right, you could actually describe the system in as some kind of a Boltzmann equation. Like you can understand Fermi liquids and metals as in terms of Boltzmann equation of electrons and holes. And then, yeah, it is possible to do that. And then this imaginary part is basically what you call in Boltzmann equation something called relaxation time. If you have seen, if you have studied Boltzmann equation in your at some level, but this relaxation time now depends on the momentum. It's a momentum dependent relaxation time. So if you have seen the Boltzmann equation in the relaxation time approximation, this is what gives us relaxation time. But however, if z goes to 0, right, you cannot describe the system at all in terms of any Boltzmann equation. This becomes a completely so the question is, how will you, so any usual kinetic pictures breaks down, or usual kinetic pictures are not relevant. Kinetic pictures don't work. And there are something very remarkable. People have been able to show that there are certain systems where this can happen, where the total, where there is this, that z becomes exactly 0 in this. You can take the most strongly interacting limit, and in such limits, it turns out you can describe the system in an alternative way, which is rather something called ADS-CFT duality or holographic duality. So what happens is, so for zk equal to 0, when all quasi-particle picture breaks down, you have some system here. This is original system, which is quantum, extremely quantum regime. Why extremely quantum? Because the interactions are so strong that even the basic fundamental classical approximation breaks down. So, and you cannot even have a starting point. A classical description is not even a starting point to say anything about the theory. So then you can replace it by some classical gravity description. And this classical gravity is typically Einstein's gravity coupled to a few fields. So it basically becomes a classical gravity problem. And a black hole here would describe a thermal state, for example. And perturbations of the black hole would give you hydrodynamics, transport, and stuff like that. So what happens is that you can alternatively describe the system in a totally different language. It's called, this is what is called the holographic duality. And it has been proven to work in certain cases, in certain systems. There's no general thing that's always valid, or unlike the Boltzmann equation, is certainly always valid. It's not quite clear where such a thing would work. There are good reasons to believe in lower dimension it always works. So if your system is only 2 dimension, 1 space, 1 time, that is 1 + 1 dimensional system, and in certain limits, this should always work. There's some good reasons to believe, but in general, it's not quite clear whether that's the right kind of way, or maybe it's a more complicated version of some classical gravity, which we don't know yet. It could be a little bit, yeah, it could be what people suspect it may, yeah, typically what one suspects is not exactly Einsteinian classical gravity, but it's something more complicated than that. But still, one would believe that something like this should be generally valid. And in that case, you have, now you might think that, okay, first of all, this system is totally quantum and this is classical. How can a classical system give rise to a quantum system? And how do you see the, so the point is that in classical system, there are this, when you think of these recombinations, you get some meaningless infinities that you have to subtract out. And here, what you get in classical gravity is that you need a negative cosmological constant, lambda. That actually tells you that this is very highly warped space. So the volume as you go towards the boundary increases infinitely. And therefore you have to put, so basically if you're living in such a space, you would actually almost see it as one dimension less, because the volume is increasing very fast in the radial direction. So so basically it's like a saddle where this other dimension, most of the volume is towards the boundary. It's like this saddle kind of, so most of the volume is towards the boundary. So you basically see only one dimension. And now you have to do some kind of, when you actually evaluate the classical action, that also is infinite. And you have to do something, just the usual GR like thing. Like if you are studying GR, what you have to do, you have to find analog of the surface currents. There's something called a surface stress tensor. So which you have to regulate. You have to first cut out a slice which is not exactly at the boundary and something, and then do something limit. And in that process, you actually produce all this kind of quantum effects. Although it's purely classical computations, you're able to reproduce all kind of quantum subtleties through these classical computations. This is really remarkable because it's a very deep GR computation. It's a computation in bona fide general relativity. And then lo and behold, all of these classical GR computations can reproduce all the subtleties of quantum theory, including extremely subtle things. And people have checked by doing computations where sometimes you can do computations both in the gravity side and on the quantum system. Some of the computations are possible, and whenever you can do that, they exactly match, and that's almost miraculous. So that is a beautiful thing that people can do. So all that I'm trying to say is that my point is that it is, so it's a very beautiful topic, and like what happens when you interpolate Z. But so usually in this course we'll be always in this limit when Z is closer to 1, right? When Z is closer to 1, that will be the limit that we will be operating here. Okay, so basically this gives you already an idea of how things look like in an interacting theory. But as I said, we would give a very rigorous proof of the Feynman propagator, and then it will follow that retarded propagator should also have a similar structure. It will follow from there. Yeah.
Is Z independent of sigma, or is it dependent on sigma and somehow?
These are two different functions. They come out from the same computation of the Feynman diagrams.
Okay, because it would look like if you have a theory where interactions are more, then lifetime of a particle you would expect to be less, right? So
that is a good question. So you would expect, that's another very interesting thing. Thanks for asking this. Actually, what turns out is there are many things that are happening here. Actually, it is a little bit. Yeah, I think I don't know how to say this in a most clear way. So what happens is as follows. Although your Z goes to 0, it's very interesting that this imaginary sigma k may not actually go to 0 or may not go to infinity, right? You would expect that more and more interactions are strong, this will go down and all this thing. What happens is something remarkable, that this is often called Planckian dissipation. This is a term that has been coined by Subir Sachdev in Harvard University. What happens is that this imaginary sigma k, this actually becomes of the order of the temperature T. And so the lifetime, if you say the lifetime, that goes like h bar by T or h bar by kt, if you wish, if I reinstate the k, up to some factor f, which is order 1, which is independent of all the parameters of the theory, or it's something like it's a universal thing. So here, the lifetime comes only from the temperature, or that sets the scale of how long particles can live, not the interactions or no coupling constants or anything. It's simply set by the energy scale of the system itself. So if the temperature goes to infinity, then of course the particles don't live at all, but that's not a big surprise. But if the system has a finite temperature, then there's still kind of, these collective excitations have still a finite lifetime. And this actually is something that is supposed to explain some very strange properties of strange metals, which I don't want to get into. But this is very interesting that this Planckian dissipation is also a very natural consequence of classical gravity picture, because in that case, it's a black hole horizon, and there's something called the membrane paradigm in general relativity that you can understand a lot of stuff just by looking at the near horizon behavior of the geometry. It's a horizon of the black hole that controls dissipation. So and the Hawking temperature that is the surface gravity of the black hole horizon, that is what controls this kind of lifetime of particles. So basically, this is something that is actually also consistent. But when Subir gave this kind of things, it was actually much long before even these things were stated. He was trying to argue for this picture much earlier, actually, than people came up with the holographic duality. But simply, but anyway, but this is all fascinating, right? And one way to do it is that we would try to understand and interpolate this system all the way like this, how some quasi-particle picture breaks down, and then how to describe this quantum soup, right? And that's one of the most beautiful problems. If you could find a way to interpolate all the way from here to here and develop a clear understanding of that, then actually this would be like one of the big problems, solving one of the big problems, open problems in quantum field theory today, how to interpolate between this. But interesting, okay, this is one of the things, for example, I work on, but I'm not going to tell you about what ideas people have come up with, because that's going to be something well beyond this course. I just wanted to introduce you to the idea that there are descriptions also possible when this quasi-particle pole completely vanishes. But as long as it doesn't vanish, you have something called a you have the notion of quasi-particles in the system. We will come back to this later in the context of Fermi liquids, which we can include in the course at the later stage. But for the moment, this is all I want to say about the general structure of retarded. So I make a big jump now from this thing, but at least you have an intuitive feel why it can happen, right? I think it's very important to get intuitive feel of your computations before you actually know how to compute them. And I would, as I said, what I will do, my plan would be to show you first how to do these computations and get a structure of this form. And then I will give you a non-perturbative proof, a complete proof in quantum field theory that it has to take a structure of this form. But the easier thing to do would be in the context of the Feynman propagator. But then it will be obvious that the retarded propagator and Feynman propagator are related to each other. And therefore, you should have this kind of a structure for the retarded propagator. So today, what you learned is the notion of quasi-particles and all of these things. Okay, so this is the most important, one of the most fundamental notions of quantum field theory, the notion of a quasi-particle. All right, let's try to move ahead now and into the other things. So yes, so last time I also asked you to look into this GXX, the Feynman propagator T, which is defined as minus I theta T and expectation value of XT X0, right? And minus I theta minus T expectation value of X0 XT, right? This is something that this is time ordered propagator, right? So minus I T. If I write it down, it will be like this, right? And this is something that we saw for the harmonic oscillator, what it is. And I think what we got was this was for the harmonic oscillator. This was minus I h bar by 2m omega naught mod t. Okay, now I expect you to do this and don't And please do it, because again, if you don't do it, will get slowed down. So this would be then minus I pi h bar by m omega naught. And let me see if I, sorry, let me, 1 second. Sorry, I think, let me, if you do it properly, the answer is h bar by m, and then you should have 1 by omega square minus omega naught minus I epsilon square, and then 1 minus e to the power minus h bar omega naught by t, and then you have minus of 1 by omega square minus omega naught plus I epsilon square, and 1 by e to the power h bar omega naught by t minus 1. But if you look into it carefully, this is what I showed you as give you as an exercise to do. So try to do it, this part at least. Try to do it by next class. So the only trick that you have to take into account is a mod t. So try to think what you'll do with this mod t. It's not hard. So you see that it's going to be e to the power I omega naught t theta t and e to the power minus I omega naught t theta minus t. So to combine these two properly, and you should get this, right? So try to do this exercise. And then if you see that this part 1 by omega square minus omega naught square omega naught minus epsilon square is essentially just your retarded propagator 1 by, if I strip off this, and then you have to have a 1 over 2 omega naught, right? So it will be something like this if I write this factor explicitly. And then I said that this is equal to, if I look at it explicitly, what this would be equal to gr omega times 1 plus nb omega, where nb omega is a Bose-Einstein distribution, and ga omega nb omega, where nb omega is simply the Bose-Einstein distribution. If you wish, I can write down omega naught by 2 minus 1. Okay, so this is, so it will be like this. Okay, so now we also saw that when t goes to 0, this goes to theta minus omega minus of theta minus omega, right? So when t goes to 0, the Feynman propagator becomes gr omega times theta omega, because 1 minus theta minus omega is theta omega, right? So 1 is theta omega plus theta minus omega. So 1 minus theta minus omega is theta omega, and plus, because there's a minus sign here, so it becomes ga omega theta minus omega. So essentially, it means that you have for omega greater than 0, you have the causal response, and for negative frequencies, you have an advanced or anti-causal response. So another way to see this is as follows, that, so let us look here what is happening. So you see that for the gr omega, you have basically these two poles, right? Omega naught and minus omega naught. So what you do for gr omega is that you shift both of these poles downwards. And this is what is reflected here, omega minus omega naught plus I epsilon and omega naught minus. We have shifted both of this pole downwards. For the advanced response, what you do is that you take this and you shift both of them upwards. For the Feynman propagator at t is equal to 0, for the Feynman propagator at t is equal to 0, you shift the positive pole downwards and this other poles upwards. So for omega greater than 0, for the pole that has positive frequency has retarded response, and the pole that has negative frequency has advanced response. Now, if you look into it, all of these have the same, satisfy the same equations. So gr omega explicitly is equal to theta t times minus theta t times sine omega naught t, right? GRT. And if I look into what is del t square minus omega naught square of GRT, what should I get? So this is a thing that we were doing last time. If I take the first, so it should be del t, and then I take the first derivative, right? If I take the first derivative of t with respect to t, I get minus delta t times sine omega naught t, right? But minus delta t times sine omega naught t is 0, because when t is equal to 0, whatever is there vanishes. So I can omit this, and I only take the derivative here. So I get minus, if I take derivative of sine, I get minus omega naught theta t cos omega naught t, right? And then minus omega naught square of the same thing, theta t sine omega naught t. Okay. And then when I take another derivative here, I get, again, derivative of cos will become sine, right? So I get omega naught square theta t sine omega naught t, and then minus of this object, which cancels out. But I also have a derivative here to take of the theta, and I get minus omega naught delta t times cos omega naught t. But cos omega naught t at t is equal to 0 is 1, so I can simply replace it by identity. And so it is simply minus omega naught t. So what I get is that this satisfies this equation, del t square minus omega naught square gr t is equal to minus omega naught delta t. Yeah, so if there was a 1 over omega naught, that would have been a bit more perfect, but I think this minus omega naught is fine. It requires, it comes from some dimensional reasons, but let's, yeah. So this is equation that is satisfied by the retarded propagator, right? And actually, this is exactly the classical equation that you should have. So what you do is that when you solve for a classical problem, so you want to solve x dot double dot minus omega naught square x, right, is equal to some force. What will you do? You will basically try to solve for this, for a Green's function. GR is equal to some delta. Right? So this is GRT. And once you solve for that, then x of t should be equal to g of r t minus t prime f of t prime, where t prime is integrated over t prime is equal to minus infinity to infinity and dt prime. So this is the integral that you need to do. Yeah, I don't know why I'm not getting this correct. Why getting extra minus omega naught? I'm wondering if somehow I missed some. I missed when I load this. If I missed something, let me take a look. In real time, GR. Actually, yeah, I did miss something, and that was okay. Sorry. Yeah, okay, I actually missed something. This is h bar by omega m omega naught, of course. Yeah, this is something I wrote last time, but I didn't write today. So there's an h bar by m omega naught. There's an h bar by m omega naught. And actually this also, this is an mx double dot minus omega naught square. So there has to be, So if okay, let me see h bar by m omega naught, and this omega naught square. So yeah, here of course, anyway, this gets cancelled out, h bar by m omega naught, just to multiply by the whole thing. So then it becomes h bar by m delta t, right? And here, so yeah, so essentially I get a minus h bar by m delta t. So if you see that the correspondence between the classical gr classical, and the quantum gr is simply with an overall 1 over h bar factor, right? So that takes care of the classical quantum correspondence. But otherwise, even in the classical case, you have a m, overall m, and this should have been m x double dot minus omega naught squared by m, but I don't know what happened here somewhere. One second. So this is m del by del t2 minus omega naught square. Yeah, I should be able to, this should be the same equation, not an omega naught squared by m, but once the way it comes about is, one second, this should be minus omega naught square x equals to some force, and I put a delta t here, and m becomes 1 over m. Yeah, that is correct. So there has to be a 1 over m factor. So I have to solve it with 1 over m delta t. Oh, I see. No, okay, okay. So this is not the equation. This is already the way I defined omega naught was that, if you remember, it was already had an m omega naught square in it. That was my redefinition of omega naught when I wrote the. So when I wrote my Hamiltonian for the particle, you remember I wrote it as p squared by 2m and half m omega naught square x square, right? That's the way I wrote my original Hamiltonian. So which means that there's already a factor of m when I look at the force equation, right? So this gives me this equation. This is the correct equation to solve. So basically then in the classical problem, I get exactly the same equation, right, with a 1 by m, right? The only thing the quantum problem has is that it has this extra h bar, minus h bar. And this is the extra minus h bar is there in, as a, if you remember, if you remember this calculation I did earlier between quantum and classical, so that exactly has this minus h bar, right? And that comes from the fact that you take a commutator and you replace it by minus ih bar, essentially, when you go to this theory, or sorry, yeah, minus ih bar, and then the classical commutator becomes the quantum, sorry, it's ih bar, not minus ih bar, and then the classical commutator will become the quantum commutator will become the classical commutator, which exactly is what you get in the classical problem. And therefore, so the classical and quantum calculation are the same for the harmonic oscillator also, right? Like for the pre-particle. Now, when you compute the retarded response here, it is very important that when you solve for a Green's function, you have to know what is the Green's function is about, right? What problem you are solving, because different problems will have different Green's functions. So here, in this case, what you're looking for that you're looking for a causal response, right? Which would mean that GR T is equal to 0 for t less than 0, right? That's a very important condition. And that gives you a unique solution for this, which is exactly the same as theta t sine omega naught t. It's useful to see that how it happens, if you wish. So firstly, you can write a general solution of this guy as a superposition of cos and sine, right? So in general, you could suppose I want to solve this equation. How should I do? I will write GRT as SA cos t, SA cos omega naught t plus B sine omega naught t. And this is equal to for t less than 0. And I will say that because there's a delta function here, I have to be careful. So I will have some A prime cos omega naught t plus B prime sine omega naught t for t greater than 0. Now, whatever it is, I should have continuity, right? So first of all, for t less than 0, this vanishes for all times, right? So because it vanishes for all times, both A and B has to be less than 0. Otherwise, this cannot happen, right? So this is equal to simply 0 for t less than 0. That's what we require. And then you have this for t greater than 0. But at t greater than 0, the function has to be continuous because there are two derivatives here. If the function is not continuous, I cannot take the two derivatives. The first derivative can have a discontinuity that gives a delta function, right? Okay, I will explain that later. So now the thing is, you have seen this already. So then if it is continuous, then it should have that A prime. If I set now GR, so we should get the condition that A prime should be equal to 0, right? So that GR t is equal to 0 plus is 0 also. That implies A prime is 0. So therefore, I should have only B prime. Now I have to fix this B prime. How will I fix? I simply fix B prime by integrating this equation from minus epsilon to epsilon. I integrate this equation from minus epsilon to epsilon dt of del t square grt, and that should be the integration of minus epsilon to epsilon of 1 over m delta t dt. Now this gives me simply 1 over m. And here, what I find is that if I take a derivative here, del t, so this will be simply the jump in the derivative, first derivative of gr. So gr dot t at epsilon is equal to 0 plus to epsilon is equal to 0 minus should be equal to 1 over m. Now, when I go to epsilon is equal to 0 plus, I should simply take a derivative here. I get b prime omega naught cos omega naught t, but it is t goes to 0. Whereas if I go from the other way, it's simply 0, right? There's no derivative vanishes. So I get this simply that b prime omega naught is equal to 1 by m, and that sets the b prime to be 1 over m omega naught. And so, yeah, I don't know what happened. Oh, sorry. Maybe I have. Okay, I don't know what. There must have been some stupid error that I did because I verified everything here. So yeah, so okay, there's the m omega naught square. That's oh, there is no m because it is overall m out, and yeah. I don't know what what. Well, what I showed, both of them will satisfy the same equation, right? Without an h bar. That's what I verified. So here I must be doing something stupid. Del t square is 1 over m. And therefore, b prime is equal to what I said is b prime should be 1 over m omega naught. B prime is 1 over m omega naught. Yeah, no, that's exactly what I have here. Sorry, that's exactly that. That was the, so this is the classical answer was okay. So yeah, that's correct. Now the question is whether it's plus or minus. The plus, okay. So the classical answer is that gr classical, if I should be 1 over m omega naught theta t sine omega t, right? Sine omega naught t. Whereas the quantum answer is simply minus h bar m omega naught theta t sine omega naught t. But this is exactly the classical and quantum correspondence because it's you have to put a minus h bar extra. Right, so this is the same problem that we solve in classical mechanics to get a response to a force, right? It's the same kind of retarded function. But if you see that a Feynman propagator also satisfies the same equation, right? So let me show that to you. and this is going to be also very important for us. So let us say the Feynman propagator gxxt is equal to minus I theta t of xt x0, right? Expectation value, and plus I theta t, or sorry, minus I theta minus t of xt x0 xt. Okay. So now let me see what I get if I take a derivative of the Feynman propagator. I'll just see whether let's verify explicitly that it satisfies the same equation. If I take a derivative of the Feynman propagator, the first term is simply minus I delta t xt x0, right? And then the next term would be minus I plus I delta t, because the theta of minus t, theta t's derivative is delta t, but the theta minus t derivative is minus delta t, right? Of xt x0 xt. That's easy to see because theta t jumps like this and theta minus t jumps in the other way. So it's a negative discontinuity, it's a positive discontinuity. So now you have to simply take t is equal to 0, right? If I take t is equal to 0, then the right hand side is the same, simply x square 0, right? So these two terms actually will cancel out if I take a derivative of theta. So these two terms cancel out. So basically I have to take a derivative here of x. So in that case, I get minus theta t of pt by m x0. I'm using the Heisenberg equation of motion for xt. And then I get, I'm doing now operator calculations, right? X dot t is equal to p by m, pt by m, and x double dot t satisfies minus omega naught square xt, right? I just have to use this. These are the Heisenberg equations of motion for x. And then I get here from minus I theta minus t and x0 times pt by m. Okay, so 1 second. Let me see something. Okay, I'm fine. I think this is the correct thing. So now let me take a derivative again of this thing, right? What should be del t square gxxt, right? So again, I can take derivative of the theta first. If I take a derivative of the theta, here I will get delta and here minus delta, right? So I get minus, this should be minus I delta t, and then I get a 1 over m and a commutator of pt with x0, right? Why? Because here I get delta t and here I get minus delta t, so I could take a minus sign. Okay. And then of course I would get a derivative of p, but p dot t is equal to minus omega naught square x, right? So here I get minus theta t omega naught square xt. Okay, there's a plus because xt x0, and plus I theta minus t omega naught square x0 xt. But these two terms simply combine into minus omega naught square. Oh, sorry. Yeah, minus omega naught square or plus omega naught square gxxt. What? I think, yeah, it is minus omega naught square. But I should have got plus. I don't know why I'm not getting plus minus omega naught. Okay, the first, let us look at the first term. So again, because delta t, only t is equal to 0 is important. So here what I get is the commutator of P and X, right? What appears here is a commutator of P0 and X0. And what's the commutator of P0 and X0? It is simply minus I, right? Minus I H bar. So here, the only thing that contributes is a minus I H bar. So this is again becomes nothing but minus H bar by M. The whole thing becomes minus H bar by M. So the point is that I think okay, if I put all the signs correctly, I don't know what is happening, but yeah, I think yeah, if I put everything correctly, I would have seen. I think it is del T square omega naught square d x x t is the same equation that is being satisfied as a retarded propagator. It's minus h bar by m delta t. So the Feynman propagator and retarded propagator satisfies exactly the same equation, right? It is what the answer is different simply because you're answering a different problem. Now, this problem is not a problem of how you respond to a force. This problem, I think I have to connect my Mac to a battery, otherwise it's going to sleep. Okay, it's in charge now. So it's a solution of the same differential equation, but what actually the time order propagator is doing, the time order propagator is, as we explained, can be understood as a response of a density of a transition matrix that you take from one state to another state, and you look into the response of that. Here in this case, simply vacuum to vacuum, or you start with a thermal density matrix, it stays a thermal density matrix after some time, and or after infinite time, and then you give a perturbation at these two at these 2 points. So essentially, this is where at 2 points, at 0 and t. So this is how the response comes about. So you see that so it's the answer to a different question, right? Not the so.
But with no
So one
classical
way,
analog.
yeah, well, there is no such classical analog in a
Of
way,
Feynman.
but may not be completely true though.
Okay.
So essentially, what I would like to say, suppose you're doing it completely in the vacuum, not at t is equal to 0. This is where the thing. This is where this interpretation is correct, because if it's not t is equal to 0, this is not true, right? You only put, because you see that the general answer was that the retarded propagator had this 1 plus n. The retarded propagator has this weight of 1 plus nv, and which becomes exactly theta omega only when t goes to 0. So let us take the vacuum. So you start with the vacuum, and there are some interactions in the theory, and you wait, and you take u epsilon or u minus infinity to infinity. You evolve the vacuum. Sorry, minus infinity to infinity, and then with the delta h, where the perturbation goes like et times xt, right? And then you look into delta of this transition amplitude. Let's call it S00. So delta S00 we showed is, or delta of log S00, we showed to be equal to, essentially you have to do this integral dt et 0. This is simply a statistical, suppose it's a random field with some statistical power, and then you have this gxxt. That's what you have to do to get this amplitude. Remember, that's what we showed explicitly, that you have to integrate a plus order epsilon e to the power 4 or some higher order terms. So we showed that if you look into this, if you go back to the notes, you will see that's what is implied. The only thing is that here I'm taking an average because I'm saying that ET is a yeah, you can think of this like as a fluctuating field which has overall power, and this would be the general change in the transition amplitude that you should get. So so this is an answer to a different problem, which is not the same as a. Now, does this have a classical analog? Well, yeah, indeed, this also has a classical analog in a way, but not quite, because let me see if that is true with this. So in a classical, what happens is as follows: if this is a probabilistic field, like ET is a probabilistic field, you can think that way. So there'll be still, suppose it's a random field of some kind which has zero. So you could think about what is the probability amplitude stays in the ground state after this thing. It may have some classical analog too. There might be a good H bar goes to zero limit. So certainly, if you look at a usual scattering problem, if you look into a usual classical quantum scattering amplitude correct S matrix computation, there is a classical analog of that simply goes to classical scattering problems, right? Because two electrons, like a shoot an electron through some nucleus, right? It's rather, but that's actually basically that was a classical computation. Nobody had quantum field theory then when Rutherford did the original computation. So it is actually a, yeah, it has a classical limit. It's not like it doesn't have a classical limit, but it's an answer to a different question. It's an answer to a scattering, or so here in this case, change in the scattering amplitude, or the change in the scattering that happens because of this. All right, so I think this is that's all. Of course, in the classical case, you don't have a notion of amplitude or probability. It's simply a definite answer. But the point is that to keep in mind is that what you always do when you try to study a classical problem of this kind is that you're always talking of a beam or of a flux, right? It's not a single particle that you're talking about. So in that case, it is not so different from the quantum calculation as well, because it's about how, like, what is if it is in this direction, what is, how much of the flux goes in that direction, how much, because we are speaking of a beam of particles going through the atom or a nucleus, for example. Some of them goes in that, some of them goes in. So you have some division of the flux in various directions, right? And that comes from the understanding that you have some kind of plane wave like thing and going. So you already, so basically it's not exactly a classical computation, it's a semi-classical computation, because anyway, you're thinking of a wave function propagating through some kind of the problem that you're solving is a wave function probability for some potential. And it gets scattered. That's a classical. That's actually a quantum problem in a way, but in a different sense. Actually, normal quantum mechanics is like a classical limit of quantum field theory, because you strip off the H bar by n factors. So that's the right kind of way of thinking about it. And so anyway, I'll make some comments on this later when we actually do scattering computations. There'll be something called the Born limit, where you are recovering many of this usual calculations, usual kind of classical type calculations. So anyway, so this is basically the difference between the Feynman propagator and the retarded propagator.
Yeah. Yes, sir. You can continue. Sorry.
No, I am finished. You asked the question.
No, I was saying the Born limit. You already made that Born approximation while you taught S.
Yeah, that's exactly that. Yeah. So that would be the approximation I would be talking about. Yeah. When we do an explicit computation, we'll come back to it again. Yeah, it will be important because some of the Feynman diagrams, when you see a multi-particle state, you have to do this exchange, and we will see the Born limit explicitly there. How it comes to Feynman diagrams. Yeah.
So, but
okay, so
we have still not like done anything, any like concrete problem, right? Like we still have the tools, I think.
look, here you have to be really very patient to learn a subject like quantum field theory. You cannot just learn to do computations in a day, right? I mean, it's a crown of physics. It's a very it's a extremely subtle subject. It is not something that you just simply, okay, you can teach it like that, but then you will not understand it. I mean, you will know how to do some computations, but they will not know exactly what they mean, right? Like this notion of quasi-particle is a very fundamental notion. And if you look into any like usual quantum field theory textbook written before like modern times, they don't there are many bodies textbooks which has this notion of quasi-particles, but not there in like books. Like if you look into Spechkin's-Schroeder, there's no quasi-particle. You won't find it anywhere there. You find the Callen-Lehmann representation of a propagator, the Feynman propagator, but there doesn't talk of quasi-particles. But this is a very important concept. I mean, you cannot, in modern days, you cannot just simply learn quantum field theory without knowing the concept of quasi-particle. It will be useless, because nowadays nobody learns quantum field theory to do scattering matrix computations, for God's sake. That's not the object of quantum field theory anymore. You have a totally, it has very diverse use and diverse thing. I mean, this is, so you have to learn it for modern times. So it is, because if you just look at Peshkin-Schroeder, I can teach you a course based on Peshkin-Schroeder. So it's going to be practically useless for you. So this is, it's important to learn the concepts. And if you, so far, I think the point now is to first you have to slowly get into it, right? So at the moment, we are learning how to do the computations in a pre-field theory. That's already a lot. And then, and do the exercise before you come on Saturday. So next time we would try to pick up a pace on Saturday, and I think in the next class I will be able to complete all I need to complete before going to Wick's theorem and telling you how to do the general computations. But there are many such subtleties here which will get slowly clear. So I try to. So I think it's very important to understand intuitively what the results are first, and then go for rigorous proofs and sometimes. So this Callen-Lehmann representation, I will give explicit rigorous proof. And it's easier to start with the Feynman propagator and give a general structure of the proof. But then Feynman propagator and retarded propagator simply related by analytic continuation like this. I mean, you simply take all the poles of the Feynman propagator like this and move it here. And that's rather simple. And there's similar trick. There's explicit way to go from a Feynman propagator at zero temperature at least. And this will actually, and then at an arbitrary temperature, I already showed you a general relation. So this relation is very generally valid, which I'll prove in the next class. That G omega is GR omega times 1 plus NB omega minus G omega NB omega. So if you know the some kind of representation of some kind of non-perturbative structure of this Feynman propagator, you automatically know all of these. We will see why, because the reason is that, okay, we will see that these three things are related by analytic continuation explicitly in a more general way. And so this is the topic of the next lecture, is to see this analytic properties of these three things in a general interacting theory and what's the structure it will take. And we'll also talk of the Euclidean propagator in the next class, okay? So try to prepare good notes. Yeah, and let us not talk about the notes. Let me finish complete the stop recording.